Today we have a couple of really nice infinite series, and the solution developments for both of them are quite satisfying. So let's call the first sum S sub 1 and the second one S sub 2, and we're going to solve them using some wonderful complex analysis. So starting off with S sub 1, we know that we can express the sine of n as the imaginary part of e to the in using Euler's formula. So this implies that S sub 1 equals the sum over the non-negative integers n of the imaginary part of e to the in divided by n factorial. And because this imaginary part operator is a linear one, we can write this as the imaginary part of the sum over the non-negative integers n of e to the in divided by n factorial. The structure of the sum is quite suggestive of a result from calculus. Now we know that if we have the sum over the non-negative integers k of x to the k divided by k factorial, then this infinite series is in fact the exponential function. Okay, cool. And if we write e to the in as e to the I to the n, we have the exact same structure, right? We have the sum over non-negative integers of something to the n, which is your index variable, divided by n factorial. So that means you have the exponential function with x being equal to e to the I. So all of this implies that S sub 1 equals the imaginary part e to the I. And using Euler's formula, we know that e to the I is the cosine of 1 plus I times the sine of 1. And now using the properties of the exponential function, we have the imaginary part of e to the cosine of 1 times e to the I times sine of 1. And one more application of Euler's formula gives us the imaginary part of e to the cosine of 1 times the cosine of sine of 1 plus I times the sine of 1. Okay, cool. And since we were interested in the imaginary part of this implies that our sum, which is the sum over the non-negative integers n of sine n divided by n factorial, equals e to the cosine of 1 times the sine of 1, which is a pretty nice result indeed. Now, the sum S sub 2 is a bit more interesting, and the first term here corresponding to n being equal to 0 is a limiting case. So S sub 2 equals the limit of sine n by n as n approaches 0, plus the sum over the positive integers n of sine of n divided by n. And we know from basic calculus that this here is famously equal to 1. Okay, cool. So we're interested in the evaluation of this sum now. The sum over the positive integers n of sine n by n. And we have a similar structure to this once again. We have a result from calculus that provides a similar structure. But first up, we know that we can write this as the imaginary part of the sum over the positive integers n of e to the in divided by n. And once again, we can write this as e to the I to the n. And the similar result from calculus that I'm talking about is the fact that the natural logarithm of 1 minus x, the reciprocal of 1 minus x, equals the sum over the positive integers k of x to the k divided by k. And we can write this using the properties of the logarithm as negative log 1 minus x. Okay, cool. So judging by the structure of our sum, we have x being equal to e to the I. So this implies that S sub 2 equals, now the first term was a 1, and the second term is going to be a negative log 1 minus x, which is e to the I. And we need the imaginary, we need the imaginary part of this, right? So we need the imaginary part of the logarithm of 1 minus e to the I. Okay, cool. So how exactly are we going to separate this logarithmic term into real and imaginary parts? Well, if you guessed polar forms of complex numbers, then you're right. So let's write our complex number z as 1 minus e to the I. And again, using Euler's formula, we have 1 minus the cosine of 1 minus I times the sine of 1. Now for the polar form of z, we need the modulus of z times e to the I times the argument of z. Okay, cool. So the modulus of z equals the square root of the square of this real part, which evaluates to 1 plus the square of the cosine of 1 minus twice the cosine of 1, and the square of the imaginary part, which is the square of the sine of 1. And sine square and cosine square add up to give you 1. So you have 1 plus 1, which is 2. Okay, nice and easy so far. And you can simplify this further, since we know that, we know that cosine of 1 using the double angle formula can be written as 1 minus twice the square of the sine of 1/2. So multiplying by 2 will give you 2 minus 4 times the squared sine term. The 2's cancel out, and so do the two negatives give you a positive. And this implies that the modulus of z equals twice the sine of 1/2. Okay, that's pretty neat. And as far as the argument is concerned, well, the argument of z equals the inverse tangent of this imaginary part here, which is negative sine 1, divided by the real part, which is 1 minus the cosine of 1. And because the inverse tangent is an odd function, we can just write this negative sign outside here. Okay, cool. So we can simplify this again using double angle formulae. So this implies that the argument of z equals the negative of the inverse tangent of twice the sine of 1/2 times the cosine of 1/2, and downstairs you have 1 minus the cosine of 1. So that gives you twice the square of the sine of 1/2. So you lose out one sine term upstairs and downstairs, and you're left with the 2's canceling out as well. So cosine 1/2 divided by sine 1/2. This implies that the argument of z equals the negative of the inverse tangent of the cotangent of 1/2. And there's a really nice relation between tangents, inverse tangents and cotangents that's going to come in handy. We know that the inverse tangent of x plus the inverse cotangent of x equals pi by 2. So this implies that inverse tangent x equals pi by 2 minus inverse cotangent x. And replacing x by the cotangent of pi by 2, we get inverse cotangent pi by 2, inverse tangent of cotangent pi by 2, that is, equals pi by 2 minus the tangent and the cotangent cancel out, so you're left with 1/2. Okay, cool. So we have the argument of the complex number as well as the modulus. So this implies that z, which was 1 minus e to the I, equals twice the sine of 1/2 times e to the negative I times, oh, sorry about that, I just evaluated this, negative I times pi by 2 minus 1/2. We now have all the ingredients required for the evaluation of S sub 2. So this equals 1 minus the imaginary part of log of this complex number, which in the polar form quite nicely sorts out to twice the sine of 1/2 times e to the negative I times pi by 2 minus 1/2. Okay, cool. And using the properties of the logarithm, we can write this as 1 minus the imaginary part of log 2 times sine 1/2 plus log times e to the negative I pi by 2 minus 1/2. And the logarithm and the exponential function here are inverse functions, so they cancel out nicely, and you're left with 1 minus the imaginary part of log 2 sine 1/2 minus I times pi by 2 minus 1/2. And we're interested only in the imaginary part, so this implies that s sub 2 equals 1 plus pi by 2 minus 1/2. And we know the 1 minus 1/2 is 1/2. So this implies that s sub 2, which is the sum over the non-negative integers n of sine n by n, equals 1 plus pi by 2, which is again quite a nice result indeed. Anyway, I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.